Well, hi and welcome to differentiating trig functions. I'm going to talk to you today about how we differentiate trig functions and also why we get the results that we do. So let's have a look at this now. There's our title. Trig obviously could or probably should be trigonometric, but I'm a little bit lazy, or periodic. Let's start with our function y equals sine of x. And this is a good place to start because if you start with cos x, it just does something a little bit strange, a little bit different, that makes it a little bit harder to understand. So what I'm going to do is have a look at this graph that I've pre-drawn. This is the y equals sine x graph, and hopefully you recognise it. It obviously carries on here, but this graph follows like that and reaches a maximum there, which is a maximum of 1, and a minimum down here of -1, and it looks a bit like that. Okay? If we're differentiating sine x, the main thing you have to remember is that when we determine the value of dy dx, that is a rate of change function. That's what we're calculating. On the graph, that means we're talking about the gradient. So let's investigate what the gradient looks like. Okay? So, first of all, let's start with the obvious ones. The obvious ones are the stationary points. There's a stationary point, and there's a stationary point. At those points, the gradient is 0. So we have a 0 gradient and a 0 gradient there. Okay? Now, let's investigate some other points here. So I've got some interesting things happening. First of all, this gradient is positive, and that's the most positive it gets. So it's actually there, and I'm letting in a bit of a secret. The gradient for this standard y equals sine x function at 0 is 1. We can't really see from the graph whether it's 1, or whether it's 10, or whether it's 0.2. We know it's positive, and we know that's the maximum. That's all we know. As we move along our function to there, and into there, and into there, and into there, the gradient continues to be positive, but it is decreasing. So it does a bit of this. It drops down, drops down, drops down to there. Okay? Now, on this side, you'll see the gradient is negative, but it's increasing. It's negative, but it's getting steeper. So it sort of does this. And it hits a maximum about there. And then, if you track this along, it does it again, and then it becomes positive again and reaches the maximum again. And we get this function. As you can see, I've missed some of the dots, so I'm sorry about that, but the point is still true. This function here also has a minimum at -1 and a maximum, so there, at 1, but it's now the cos function. So we get dy dx of sine x is cos x. And equally, so if I start with, I'm going to make my little diagram here, sine x, the derivative is cos x, and then the derivative of cos x isn't quite what you expect. It's similar though, it becomes negative sine x. And of course if you derive sine x, you get cos x, so if you derive negative sine x, you get negative cos x. And if you derive negative cos x, you get negative sine x, which takes you back to sine x. And so we get this diagram. It goes sine x to cos x if you derive, cos x to negative sine x if you derive, negative cos x, sorry, that was really bad. And it might even be off the screen. And then if you derive that, that's what you get. Okay, now you just need to take that rule and learn to use it to differentiate a range of different functions, such as y equals x cos x. This involves periodic differentiation, but it's a product rule question. Or y equals cos of x squared. This also involves trig differentiation, but it's a chain rule question. So you're going to go away and practice that now. But you know, if you understand how to derive trig functions using this rule, and you've learnt product rule, quotient rule, chain rule using polynomials, you'll find it's not that different and you use the same processes. Anyway, all the best.